This video was sponsored by the Great Courses Plus. Space, the way we experience it, has 3 dimensions: left, right, forward, backward, and up, down. But why 3? Why not 7 or 26? The answer is no one knows. But if no one knows why space has 3 dimensions, could it be that it actually has more, just that we haven't noticed for some reason? That's what we'll talk about today. The idea that space has more than 3 dimensions may sound entirely nuts, but it's a question that physicists have seriously studied for more than a century. And since there's quite a bit to say about it, this video will have 2 parts. In this part, we will talk about the origins of the idea of extra dimensions, Kaluza-Klein Theory and all that. And in the next part, we will talk about more recent work on it, string theory and black holes at the Large Hadron Collider, and so on. Let us start with recalling how we describe space and objects in it. In 2 dimensions, we can put a grid on a plane, and then each point is a pair of numbers that says how far away from 0 you have to go in the horizontal and vertical direction to reach that point. The arrow pointing to that point is called a vector. This construction is not specific to 2 dimensions. You can add a 3rd direction and do exactly the same thing. And why stop there? You can no longer draw a grid for 4 dimensions of space, but you can certainly write down the vectors. They're just a row of 4 numbers. Indeed, you can construct vector spaces in any number of dimensions, even in infinitely many dimensions. And once you have vectors in these higher dimensions, you can do geometry with them, like constructing higher dimensional planes or cubes and calculating volumes or the shapes of curves and so on. And while we cannot directly draw these higher dimensional objects, we can draw their projections into lower dimensions. This, for example, is the projection of a 4-dimensional cube into 2 dimensions. Now, it might seem entirely obvious today that you can do geometry in any number of dimensions, but it's actually a fairly recent development. It wasn't until 1843 that the British mathematician Arthur Cayley wrote about the analytical geometry of n dimensions, where n could be any positive integer. Higher dimensional geometry sounds innocent, but it was a big step towards abstract mathematical thinking. It marked the beginning of what is now called pure mathematics, that is, mathematics pursued for its own sake, and not necessarily because it has an application. However, abstract mathematical concepts often turn out to be useful for physics. And these higher dimensional geometries came in really handy for physicists, because in physics we usually do not only deal with things that sit in particular places, but with things that also move in particular directions. If you have a particle, for example, then to describe what it does, you need both a position and a momentum, where the momentum tells you the direction into which the particle moves. So actually each particle is described by a vector in a 6-dimensional space, with 3 entries for the position and 3 entries for the momentum. This 6-dimensional space is called phase space. By dealing with phase spaces, physicists became quite used to dealing with higher dimensional geometries. And naturally, they began to wonder if not the actual space that we live in could have more dimensions. This idea was first pursued by the Finnish physicist Gunnar Nordström, who in 1914 tried to use a 4th dimension of space to describe gravity. It didn't work though. The person to figure out how gravity works was Albert Einstein. Yes, that guy again. Einstein taught us that gravity does not need an additional dimension of space. 3 dimensions of space will do. It's just that you have to add 1 dimension of time and allow all these dimensions to be curved. But then, if you don't need extra dimensions for gravity, maybe you can use them for something else. Theodore Kaluza certainly thought so. In 1921, Kaluza wrote a paper in which he tried to use a 4th dimension of space to describe the electromagnetic force in a very similar way to how Einstein described gravity. But Kaluza used an infinitely large additional dimension and did not really explain why we don't normally get lost in it. This problem was solved a few years later by Oskar Klein, who assumed that the fourth dimension of space has to be rolled up to a small radius, so you can't get lost in it. You just wouldn't notice if you stepped into it. It's just too small. This idea that electromagnetism is caused by a curled-up fourth dimension of space is now called Kaluza-Klein Theory. I have always found it amazing that this works. You take an additional dimension of space, roll it up, and out comes gravity together with electromagnetism. You can explain both forces entirely geometrically. It is probably because of this that Einstein in his later years became convinced that geometry is the key to a unified theory for the foundations of physics. But at least so far, that idea has not worked out. Does Kaluza-Klein theory make predictions? Yes, it does. All the electromagnetic fields which go into this fourth dimension have to be periodic, so they fit onto the curled-up dimension. In the simplest case, the fields just don't change when you go into the extra dimension, and that reproduces the normal electromagnetism. But you can also have fields which oscillate once as you go around, then twice, and so on. These are called higher harmonics, like you have in music. So Kaluza-Klein theory makes a prediction, which is that all these higher harmonics should also exist. Why haven't we seen them? Because you need energy to make this extra dimension wiggle. And the more it wiggles, that is, the higher the harmonics, the more energy you need. Just how much energy? Well, that depends on the radius of the extra dimension. The smaller the radius, the smaller the wavelength, and the higher the frequency. So a smaller radius means you need higher energy to find out if the extra dimension is there. Just how small the radius is, the theory does not tell you, so we don't know what energy is necessary to probe it. But the short summary is that we have never seen one of these higher harmonics, so the radius must be very small. Oskar Klein himself, by the way, was really modest about his theory. He wrote in 1926, Ob hinter diesen Andeutungen von Möglichkeiten etwas Wirkliches besteht, muss natürlich die Zukunft entscheiden. Whether these indications of possibilities are built on reality has of course to be decided by the future. But we don't actually use Kaluza-Klein theory instead of electromagnetism. And why is that? It's because Kaluza-Klein theory has some serious problems. The first problem is that while the geometry of the additional dimensions correctly gives you electric and magnetic fields, it does not give you charged particles like electrons. You still have to put those in. The second problem is that the radius of the extra dimension is not stable. If you perturb it, it can begin to increase, and that can have observable consequences which we have not seen. The third problem is that the theory is not quantized, and no one has figured out how to quantize geometry without running into problems. You can, however, quantize plain old electromagnetism without problems. We also know today, of course, that the electromagnetic force actually combines with the weak nuclear force to what is called the electroweak force. That, interestingly enough, turns out to not be a problem for Kaluza-Klein theory. Indeed, it was shown in the 1960s by Richard Kerner that one can do Kaluza-Klein theory not only for electromagnetism, but for any similar force, including the strong and weak nuclear force. You just need to add a few more dimensions. How many? For the weak nuclear force you need 2 more, and for the strong nuclear force another 4. So in total we now have 1 dimension of time, 3 for gravity, 1 for electromagnetism, 2 for the weak nuclear force, and 4 for the strong nuclear force, which adds up to a total of 11. In 1981, Edward Witten noticed that 11 happened to be the same number of dimensions, which is the maximum for supergravity. What happened after this is what we'll talk about next week. This video was sponsored by the Great Courses Plus. I'm always looking for new brain food, and while YouTube is really useful to get inspiration, it's not particularly good for providing structured educational content. For structured learning, I have found the Great Courses Plus an amazing place. The Great Courses Plus is a subscription on-demand video learning platform that allows you to stream lectures on your browser or using an app on your phone. It's like Netflix, but for learning. The Great Courses Plus have more than 11,000 video lectures from recognized experts about whatever it is that you are interested in, from science and math to linguistics and cooking. The Great Courses Plus now offers a free trial for viewers of this channel, which is a double benefit because it both serves your curiosity and supports this channel. To make use of this offer, please visit thegreatcoursesplus.com/Sabine or just click on the link in the description below and start your free trial today. Thanks for watching. See you next week.